What if an electron inside an atom behaved like a planet orbiting the Sun? Could it circle the nucleus forever, like Earth orbits the Sun? Or would it spiral inward and collapse into the atomic core? This was a question that physicists grappled with soon after Ernest Rutherford's groundbreaking discovery that atoms are mostly empty space, with nearly all their mass concentrated in a tiny nucleus at the centre. But if the nuclear model is true, then what are the electrons doing inside the atom? To see the problem, let's consider a simple classical picture of the hydrogen atom consisting of one proton and one electron. According to the laws of electrostatics, the electron cannot be stationary with respect to the proton. But why? Well, because the proton carries a positive charge and the electron carries a negative charge, creating a force of attraction. This force can be calculated using Coulomb's law, which states that the magnitude of the electric force between the proton and the electron will be equal to E squared divided by 4 pi epsilon naught r squared, where E is the fundamental unit of charge and r is the distance between the proton and electron. Epsilon naught is the permittivity of free space. Now, since this electrostatic force is the only force acting on the electron, then according to Newton's second law, it would accelerate forward towards the proton, inevitably crashing into the nucleus. Clearly, the atom would not be stable in this scenario. Okay, so the electron cannot just be sitting there stationary, but what if instead the electron was orbiting the proton, much like Earth orbits the Sun? Despite the gravitational pull of the Sun, Earth doesn't crash into the Sun because it has a tangential velocity. Essentially, Earth is always falling towards the Sun, but missing it. So it was natural for physicists to imagine that the atom worked like a miniature solar system. In this model, the electrostatic force between the negatively charged electron and the positively charged nucleus played the role of gravity, holding the electron in a stable orbit around the nucleus. However, there's a fundamental problem with this idea. As you may know, an object moving in a circle is constantly changing direction. Even if its speed stays constant, this change in direction means the object is accelerating. That's because acceleration is defined as the rate of change of velocity, and velocity as a vector includes both speed and direction. So if either changes, we have an acceleration. Now, here is where the trouble begins, because according to 19th century electrodynamics, any accelerating electric charge radiates energy as electromagnetic waves. For an electron in orbit, this energy loss would cause it to spiral inward unless there's a constant supply of energy to keep it going. Physicists quantified this energy loss using the Lamore equation, dE by dt equals minus E squared A squared divided by 6 pi epsilon naught c cubed. Here, E is the charge of the electron, A is its acceleration, and c is the speed of light. And the negative sign simply shows the energy is decreasing with time. The question is, how long would it take for an electron orbiting a proton to radiate away all its energy and spiral into the nucleus? Let's find out. So let's set up the scenario. Let's imagine an electron orbiting a proton in a circular path of radius r with linear velocity v. Now, it is the electrostatic Coulomb force between the electron and proton that provides the centripetal force required to keep the electron moving in its circular orbit. And we know from Newton's second law that this centripetal force is equal to mv squared divided by r, which is simply a statement of F equals ma, where a is equal to v squared over r. And so we have that mv squared divided by r is equal to E squared divided by 4 pi epsilon naught r squared. If we then solve this for v squared, we find the following blue expression, and we can then use this to calculate the centripetal acceleration of the electron, which, if we sub in our expression for v squared, we find that a is equal to E squared divided by 4 pi epsilon naught m r squared. We can then take this expression for the centripetal acceleration and substitute into the Larmor equation, in which case we find the following. This can be simplified, resulting in the following blue expression. Okay, next, let's calculate the total energy of the orbiting electron, which is the sum of its kinetic energy and potential energy. The kinetic energy is given by half mv squared, and the potential energy is given by minus e squared divided by 4 pi epsilon naught r, where r is the distance between the proton and electron. Next, if we sub in the expression for v squared that we derived earlier, we find the following expression, and this simplifies to minus e squared divided by 8 pi epsilon naught r. This represents the total energy of the electron for a given radius r. Next, we want to differentiate this expression with respect to time so that we can equate it with the expression we derived earlier from the Larmor equation. To do this, we make use of the chain rule to write dE by dt equals dE by dr multiplied by dr by dt. Now, we can calculate the first of these terms by differentiating the total energy with respect to r, in which case we find e squared divided by 8 pi epsilon naught r squared. If we then sub this back into our chain rule product, we find the following expression. Okay, so now we have two expressions for the derivative of the energy with respect to time, and if we equate them, we find the following purple expression. And we can then rearrange this for dr by dt and simplify, and we find the following green expression. And this is what we were looking for. We now have a differential equation written in terms of the radius and how it changes with respect to time. To solve this equation, we can separate the variables and then integrate the radius from an initial radius r equals capital R at t equals 0 to r equals 0 at t equals t subscript c, where t subscript c is the time taken for the electron to spiral and collapse into the proton. If we do that, we find the following expression. If we then integrate both sides with respect to r and t respectively, we find the following green expression, and if we then sub in the limits of integration, we find the following purple expression. Finally, if we rearrange this for t subscript c, we find the following green expression, and this is what we were looking for. We now have an equation that tells us how long it would take the orbiting electron to lose its energy and spiral into the nucleus. Now, given that a hydrogen atom has a radius of order 10 to the minus 10 meters, we can sub this value into our equation, and we find that the time taken for the electron to spiral into the nucleus is approximately 0.1 nanoseconds, which is less than a billionth of a second. Let's just pause and take a moment to appreciate this remarkable result. We have seen that using the classical laws of physics, an orbiting electron would spiral into the nucleus in an astonishingly short time, just 0.1 nanoseconds. That's an astonishing prediction, but it also highlights a glaring issue, because we know that atoms are stable. Think about it, our everyday world doesn't spontaneously collapse or fall apart. Objects retain their structure, the chair you're sitting on, the water in your glass, the air you're breathing. This stability is only possible because atoms, the fundamental building blocks of matter, are themselves stable. Yet, from our calculation, the classical picture of the atom predicts that electrons should spiral into the nucleus in tiny fractions of a second. If this were true, the world around us simply wouldn't exist. Furthermore, according to this model, as the electron spirals inward, it would emit a continuous spectrum of radiation. But experiments show this doesn't happen. Instead, atoms emit light in precise, discrete wavelengths, creating a unique pattern of spectral lines. These contradictions reveal a fundamental truth. Classical physics, elegant as it is, cannot explain what's happening inside the atom. This was one of many failures that forced physicists to a revolutionary breakthrough: quantum mechanics. It turns out that electrons don't orbit the nucleus like planets around a star. Instead, they exist as waves of probability, governed by bizarre and beautiful rules that defy everyday intuition, but perfectly explain atomic stability. Solving this mystery didn't just save the atom, it reshaped our understanding of the universe. Thank you for listening, and see you next time.